Hello everyone, welcome to Postgres Statistics and Data Science. So we'll be looking at some questions from part A of the CMI MSc entrance from 2020. So the questions will be primarily focused on inequalities and will be primarily using like seeing like what concepts of inequalities we can use to solve these questions. Also, these questions are from part A, so they are either multiple correct or single correct. So let's go ahead. So the first question says that we have four inequalities, and we are asked as to which of these four hold true. So let's look at the first one. It's given as 2019 by 2020 is less than 2020 by 2021. This is a pretty easy pattern to spot, as you can see that 2019 is nothing but one less than 2020, and 2021 is nothing but one more than 2020. So you can just make it -1 plus 1 here, and then you can do cross multiplication. So here it becomes nothing but 2020 minus 1 times 2020 plus 1. So this is equal to a minus b into a plus b. So you can reduce this to a square minus b square. So 2020 square minus 1 is obviously less than 2020 square. It is true. So the overall inequality holds. Note that I have used a bidirectional like this sign here. So this means that if this holds true, then this holds true. If this holds true, then like if and only this is if and only if. So this holds true if and only if this holds true, and this holds true if and only if this holds true, which is true. So the first state is true. So this one is correct. Let's move on to the next one. Let's change the thing. Yes. So let's move on to the next one. It's given that x plus 1 by x is greater than is equal to 2 when x is greater than 0. So this is a pretty standard result that follows from AMGM inequality. For those of you who are unaware of AMGM inequality, it goes like this: that take two non-negative real numbers x and y, then the arithmetic mean of x and y is greater than their geometric mean, which is equal to this. This is the AMGM inequality. And here we are using basically y is equal to 1 by x, and x is already greater than 0, so the non-negative part holds. So this is the arithmetic mean, and this is the geometric mean, which is just equal to 1. So x plus 1 by x, and then is equal to 2. You can also do this using using the fact that x plus 1 by x whole square is greater than is equal to 0, using the fact that any perfect square is greater than is equal to 0. Sorry, this should be -1. You'll see why I made it -1. Just give me a second. Yes, so this is 2, and this is this, right? And then you can put 2 on the other side. There you go. And the result follows. So there are two different ways of making and like proving this. So just keep it in mind. And this is a very easy pattern to spot as well. The next one is a bit difficult. We're asked to show that 2 to the power 60 is greater than 5 to the power 24. Okay. So one of the ways, like there are actually two ways to proceed with such like C and D. First one is to like somehow try taking logarithm and try using like bringing it down to basically the level of functions and try using if the function is increasing or decreasing and trying to prove it. Second one is basically equating the base or the exponent on both sides, because you know the fact that like if the base is equal, then the higher exponent, like if the base is equal and positive, then higher base will and then higher exponent will mean higher value. Also, if the exponent is same and then basically the base is different, then you can just you can look at it and figure it out. So one of the most effective ways is to just basically make either the base or the exponent on both sides of the inequality same and see what follows from there. So this is what we'll be trying to do here. And you can look at here that we have 2 to the power 60, which is nothing but 2 to the power 5 into 12. So just put 12 outside. This is nothing but 32 to the power 12. Then 5 to the power 24 also it is 25 to the power 12. This is why we equated the exponent here, is because we noticed that 60 and 24 have a common divisor of 12. So it's easier to reduce 60 and 24 to 12 rather than take 2 and 5 to somewhere, because 2 and 5 are co-prime. So you can see basically since 32 is greater than 25, it's 32 like both of them raised to the power 12. This inequality preserves as it is 32 to the power 12 is greater than 25 to the power 12. So 2 to the power 6 is greater than 5 to the power 24. So this one holds. Finally, this one 2 to the power 314, 31 to the power 40. So again, latest attempt to equate the exponents, because 2 and 31 have basically no common factors, but 314 and 42 might, like it has 2. But then again, just notice one thing, that is 2 to the power 5 is actually 32, which is one more than 31. Let's see if it gives us some hint from there. So we can break 314 into 210 and 104. The reason why I did 210 is because I want this power 42, right? I want this power 42. So notice that 42 times 5 is 210. So what I'm getting here is that 32 whole to the power 42 into 2 to the power 100 is basically this value. So I could break this in 210 plus 104, and I'm getting this. But I know that 32 is greater than 31, obviously. So both of them raised to the power 42. It's still 32 to the power 42 is greater than this one. So what happens is that after this, since this value is already greater than this, so multiplying LHS by 2 to the power 104 makes it even bigger. So it's anyways greater than 31 to the power 42. So this one is wrong. So there goes the 4 inequalities. So the key takeaway from this is that, like especially in CMI's entrance, if there is any question relating to inequality, it will come from these only two patterns. That is, um, always try to check if it can be solved with the AM, GM, HM inequalities. They're the most basic inequalities of all, most effective as well. Also, like if you see these kind of number exponent based inequalities, then always try to follow these two strategies. Try to equate the exponents or the basis. To equate the exponents and or the basis, you will basically need to choose which one of them have some common factors, and then reduce it to there. So that is the key takeaway from this question. We'll move on to the next question, which is question number 17. And this one is that says that there's an identity here, 1 by 1 minus 2r, which is an infinite series, that is summation. It is true, and under which condition? If and only if when we have four statements about values that r can take. First one says that r is not equal to half. Second one says that r is between 0 and half, can take the value 0. Third one says that it is greater than is equal to minus half and less than half. And the fourth one says that modulus of r is less than half. So this identity holds true only when the infinite series on the RHS converges. So basically, you have to find the condition of convergence for this infinite series. To do that, we'll be using the root test. Here's a root test. Root test says that, say you have an infinite series, summation of n equal to 1 to infinity. Then then calculate this limit, which is limit n tends to infinity modulus of n whole to the power 1 by n. Okay, so the term, take the absolute value and raise it to the power of 1 by the term number, basically. So then check these three. If L is less than 1, then the series converges. If L is greater than 1, then it diverges. If it is 0, then the test is inconclusive. Here we need to find when it converges. So we'll basically take the we'll basically find this limit and check if it is, and we'll make it, basically we'll assume that it is less than 1 because we need it to converge, and we'll find the range of r from there. So what is the limit in this case? See, the term is basically 2r whole to the power k. So modulus of 2r whole to the power k is nothing but modulus of 2r, like basically what I mean is this. This is the same thing as this. So I directly root this. This k and this k cancel out. So this limit nothing but limit k tends to infinity modulus of 2r. Since modulus of 2r doesn't depend on k, so the limit is basically the same as modulus of 2r. I want this limit to be less than 1. So modulus of 2r is less than 1. And so basically mod r is less than half. So option D holds this one. Also, just a heads up, this is an infinite geometric series. Infinite geometric series is converged only when the modulus of the term, like this one, what's inside, is less than 1. So you could, like, if you knew that, you could use it directly. You don't need to use root test. But if you don't know that fact and you know root test, then you have to basically know root test. And when you're preparing for the sentence, so you'll be looking at series and sequences. So it really helps to know what tests for convergence of series and what tests for convergence of sequences are there, and they'll generally help you in the exam. We'll move to the last question for this one. It says that which of the following inequalities are true, and we've got 4 of them. So look at that is the first two. First one says e to the power x is greater than or equal to 1 plus x when x is non-negative, and e to the power x is greater than or equal to 1 plus x when x is negative. So basically, it is saying that when x is at this part, e to the power x is greater, and this part is less, something like that. So we're dealing with the same functions. So one of the ways to solve these kind of questions is that take the difference of these two functions, see whether the difference is positive or negative. On that basis, you can conclude what the sign of the inequality will be. So I'm doing that fx is equal to e to the power x minus 1. Another trick is that if you have something greater than or equal to something to show, like if you say have fx greater than is, if you need to show fx greater than or equal to gx, then you should always take hx to be fx minus gx. This makes calculations easier rather than gx minus fx. So here we're doing e to the power x minus 1. Let's take the first derivative to see if it has any extreme or not. So the first derivative is e to the power x minus 1. So when f dash x is 0, x is supposed to be 0. So the second derivative is just e to the power x. So what is it? F dash, f double dash of 0, it is 1. 1 is greater than 0. So we can say that this function f has an absolute, as a global minima at x equal to 0. So it has a global minima at x equal to 0. So for any real value of x, fx is obviously greater than or equal to f0, because f0 is a minima, right? What is f0? Put x equal to 0 here. You'll find e to the power 0 minus 0 minus 1. So 1 minus 1 and 0. So f0 turns out to be 0. So fx is greater than or equal to f0 for all x in a real. So e to the power x is greater than or equal to 1 plus x for all x in a real, and especially x non-negative. So this inequality always holds. So you can see directly from here that this inequality will hold and this inequality won't. For D, so for C, let's move on. And again, in the next one, we are asked to show if 1 plus x is greater than log x or x greater than 0. So we will use the same technique. We'll take this difference. So gx is 1 plus x minus log x. Again, first derivative, that is 1 minus 1 by x. So it is equated to 0, and we will see that this is equal to 0 when x equal to 1. So probably there's an extreme at x equal to 1. Consider g double dash x, which is 1 by x square. So then g of double dash 1 is 1, which is greater than 0. So g has a global minima at x equal to 1. So these are global minima. So again, we can use the techniques we used in the previous part. The g1 turns out to be 2. You can just put x equal to 1 here. So 1, and this is 0. So this turns out to be 2. So then gx is greater than or equal to g1 for all positive x. So 1 plus x minus log x is greater than or equal to 2. This means that x minus 1 is greater than or equal to log x. Now you will ask me that this is not exactly what we set out to show. But Inequalities have these kind of finicky things where they end up with something, and to make it and to basically show what you have been asked to show in the problem, you just need to assume some very trivial inequality and extend it from there. So obviously, I know that x plus one is greater than x minus one. Like this is just absolutely simple. X plus one is greater than x minus one, and x minus one is greater than equal to log x. So this holds. X plus one is greater than log x, and so that is what basically we were asked to show in question in part C. So C holds as well. So just don't get confused if you just end up with x minus one in this case. Just look as to what should be, like, you have got one side of the inequality, right? You've got log x. So look at what should be there on the other side. Luckily for us, it was 1 plus x on x plus 1 on the other side, which is greater than what we have. So it holds. Finally, we are asked to show that e to the power x is less than x square for all values of x belong to real number. Now, you can obviously see that this term because you know that e to the power x is, like, if you take for any large enough x, then like at this that point e to the power x is pretty higher than x square. So this doesn't hold this inequality. So since you're showing that this inequality doesn't hold, just give a counter example. So easy counter example is just take x equal to 0. E to the power 0 is 1 and 0 square is 0. So e to the power x is 1 is greater than 0. So this statement doesn't hold for all x belong to 0. And actually this statement, so basically like e to the power x, it's I think, if I'm not wrong, the graph should be like this. This should be e to the power x. This is 1, and this should be x square. So basically, if you're taking positive x square is always less. It's only for negative x that is more. So just keep that in mind. So that would be all for today, and I'll see you in the next video. Thank you. Goodbye.